Good morning, everybody. Welcome to the GGI. So we are very happy to see you all today for this conference week. So this conference week is part of the 5-week program on asymptotic symmetries and flat space holography. So we are on the 4th week of the program. If you are interested in seeing the previous talks where we had the 2nd, the 3rd week, and also the talks that were delivered during the lectures, during the school, on the training week, you can find them online, either through the GGI website or on the YouTube channel of GGI. If they should all appear on this online. So a couple of announcements before we start. So today we will have a reception after the last talk. So it will be just here at the GGI just after the end of the last talk. And we have also other social events planned this week. So yeah, the next one will be on Wednesday. We have GGI is very kind enough to provide for us a free guided tour through Florence. So it's a walking tour through Florence with a guide, and we will leave together on Wednesday from here, GGI, and start the tour all together. So it's free. However, if you are interested, we still need the number of people. We still need the exact count. So we kindly ask you to write down your name on the sheet that Dario will kindly prepare for us. So please don't forget to write down your name if you're interested in the guiding tour. It's about a 2-hour walk through Florence. So that's on Wednesday. Then on Thursday, we have planned a social dinner. So let me say that unfortunately, we cannot cover the cost of the dinner. So each one will have to pay for their own dinner. It's exactly 45 euros, I believe. If you want to participate to the dinner, Dario has sent a link. I believe it was a Google form where you have to register, and you can also say if you have some food restriction there. So please do not forget to register through this form by today, because we need to have, again, an exact count of who is coming and who is not coming. So this dinner will be on Thursday, at around 8 p.m. It will be close by from GGI, and we will leave together from here. Okay, so I think that's about it for now. So now a word about the schedule of this program. So we have several talks through the days, and with this of a pretty full program. So we kindly ask each speaker to respect the time that was allocated for their respective talks. In particular, we planned this 30 plus minute or 20 plus 10 minutes format for talks. So the idea is that there is ample time for discussion. We try to have a meeting which is as interactive as possible. It's also meant to encourage the audience to ask questions during the talk. So please feel free to interrupt, ask questions during the talk, because again, the schedule was designed to allow time for that. Also, we encourage questions for maybe less experts in the audience, if they are, and also from junior participants and postdocs as well. If you have a question, please, for the sake of recording, let us know beforehand so that Dario or I can pass the microphone so that the question is recorded for the video. Okay, so I think that's about it. So we can start with the first talk. So it's an honor to have Paolo Di Vecchia from Niels Bohr Institute and Nordita, and he's going to tell us about classical observables in GR from scattering amplitude. Thank you very much.
Thank you very much. Okay, what I am going to talk about is many papers that I wrote together with Carlo Eisenberg, who is here, Rodolfo Russo, and Gabriele Veneziano. And we wrote a physics report last year where all these ideas are collected. And also 2 papers with Francesco Alessio and a more recent paper with Francesco Alessio and Carlo. And if I have time, also ongoing work with Carlo and Francesco. So this is the first gravitational wave observed at LIGO in 2015. So it's 2 black holes that rotates around each other. They have an spiral phase, and then there is a merger, and then there is a ring down. And so the discovery of this gravitational wave at LIGO generated by this black hole merging posed the problem of computing very precisely the dynamics of binary black hole merging and extract from the theory the waveform of the gravitational wave that you can compare with what you observe at LIGO. Now, most of the calculation have been done using the Einstein-Lagrangian, usually in the post-Newtonian limit. In this limit, you have a small field and also a small velocity. There is a very nice review by Luc Blanchet. Now, recently, in the last 5 or 6 years, a complementary approach has been used. So instead of starting from the Lagrangian and have all the problem with fixing the gauge and so on, one start to try to extract classical quantity from the quantum scattering amplitude using the so-called post-Minkowskian expansion. In this way, you don't have to worry about gauge. You use only quantities which are gauge invariant. Now, when the 2 black holes are far away, then the interaction is not so strong, and then you can use perturbation theory. You can expand in the Newton coupling constant, Gn. And that is called post-Minkowskian expansion. But you have all velocity. You don't have to expand. You don't have to compute in small velocity. When the 2 black holes get closer to each other, the interaction becomes very strong, and there is no way of doing analytical calculation. You have to do numerical calculation. You have to use numerical relativity. And there is a very good review by Petrorius here. Another very useful approach is the so-called effective one-body formalism, introduced by Bonanno and Damour in 1999. One constructs an effective like Hamiltonian for a particle with mass mu in the external metric that is fixed by requiring that the effective dynamics be the same as the original dynamics. And it leads to results faster than numerical relativity. And there are very interesting recently papers that I will come back to them later on. This effective one-body waveform are an important class of in-spiral merger ring-down waveform which had been used at LIGO and Virga searches. Finally, there is also what is called self-force approach. You start from a particle which has a mass much bigger than the other particle, and you study, and so this particle with high mass generate a metric, and then the smaller particle move in this metric. But then he has a back reaction on this metric, and so you have to correct the original metric, and this method is called self-force, which has been also now if you have a free-falling particle, and if a gravitational wave comes, there are 2 polarization, the plus and the cross polarization, and that is the way that the free particle structure is changed by these gravitational waves. And on this principle, one constructed the interferometer, where you have a laser sending light here, the light goes here and in this direction, and then come back. And if the two arms are the same length, then you see a certain pattern here. But if you get gravitational waves, one arm becomes smaller or bigger than the other arm, and so you notice here a different pattern, and that's the way you detect the gravitational wave. And it's very interesting that what people can detect are sides, difference in sides, which have of the order 100 of the proton dimension. So in this seminar, I will describe the two black holes as the two spinless particles with mass m1 and m2. And I consider the scattering rather than the merging. There are techniques going from the scattering to the merging, but I will not discuss them. And I will consider both the elastic and inelastic scattering with the production of soft graviton. In the case of the elastic scattering, I will show that the physical observable as the classical deflection angle can be extracted from a quantity called the diagonal, can be computed from the elastic scattering amplitude. In the inelastic case, the diagonal becomes an operator containing the graviton creation and annihilation operator. I will limit myself, in the case of an elastic process, to soft graviton, and I will describe the waveform. Doesn't work anymore. Yeah, now it's okay. Let me try. Yes. So one starts from the three-level scattering amplitude with one graviton exchange, which is given by, there is this, the propagator of the graviton, and there is the Newton constant, and there is this dependence of the amplitude is function of S and T. T is essentially minus Q squared. S is connected to the sigma here. And I consider scattering at large impact parameter. And therefore, what is important is to have the singularity at Q square equals 0. And so I can neglect terms that cancel the singularity. Now, this process involves the exchange of a single quantum, Q, which is quantum. And I will come to this, what I mean by quantum. And then one can go to impact parameter using this formula, and one gets this expression, which is called the leading diagonal, that is computed from the three-level amplitude, that is divergent for d equal 4 due to the long-range Newton potential. Now, in the classical limit, it's natural to take sigma and the length r square r, which is analogous to the Schwarzschild radius, as classical quantity, and then you can write the diagonal in this form. And the regime I'm describing is the one in which B is much bigger than the Schwarzschild, this analogous of the Schwarzschild radius and of the Compton wavelength here. Now, this delta 0 is a big quantity because in the classical limit, here. In the classical limit, there is H bar there, and for H bar going to 0, this goes to infinity. So it should appear in the exponential. So it can describe the value of the classical action. Now, Cabate and Ortiz in 92, they show that summing all this diagram, also the cross diagram, the iconal is exponentiated. And after the iconal summation, the leading contribution to the S-metric is captured by the phase, with effectively resum and infinitely many exchange. And this can be seen if you go back from the iconal, from the impact parameter space to momentum space by this formula. This formula for large B, you can use the saddle point approximation, and you get the saddle point equation. And you see that H bar cancel the 1 over H bar in the iconal, and then QS represent the momentum transfer in the classical deflection, which is also called impulse. So QS is finite in the classical limit, while Q, that was the quantum momentum in the original graviton exchange, is a quantum quantity. And then you can compute, you take the ratio of QS with Q, and Q is of the order H bar over B, and you see that the number of graviton exchange goes to infinity for H bar equals 0. So NS is very large and goes to infinity. And then from this relation, from QS, I can compute the deflection angle, which is given by this expression. And you see that now H bar disappear, and this is a classical quantity. So in conclusion, the 1 PM impulse is this quantity here. And it's now straightforward to formally generalize this discussion beyond 1 PM. One needs only to insert the full iconal here. And the question is, how do you compute the complete iconal? The iconal is extracted from higher loop diagram. So you have to remember the loop diagram contains all the also classical quantities. Now, assuming that the iconal is exponentiate, and if you go to impact parameter, the amplitude becomes this. This is the amplitude in impact parameter, which can be written as something classical, and then there is the quantum part here. And then what you have to do, you have to compute the amplitude at a certain loop order, eliminate from the amplitude the quantum part, and extract at each order in perturbation theory the contribution of the iconal. So for instance, if you expand the previous formula, at the 3 level, you get that the Fourier transform of the 3 level gives the leading iconal, then which is order 1 over H bar. At the 1 loop amplitude contains the square of this, which is 1 over H bar square. This is 1 over H bar, and this order H bar to the 0. So you have to subtract this term, which is called superclassical, extract delta 1, and that will be the 1 loop iconal. At 2 loop, you have something which H bar, 1 over H bar cube, 1 over H bar square. You have to subtract also term 1 over H bar, and then and this is the 2 loop iconal, and so on. Again, the classical deflection angle is derived from the momentum QS by this formula. Now, in the equal 4, the subleading iconal is given by this expression. And so the deflection angle at 2 PM, this is 1 PM and this is 2 PM, is given by this formula. And remember that the iconal and also this quantity Gn over E, Gn E over B, which is dimensionless, this is the expansion parameter that in the PM expansion should be kept small. Now, what about the sub-leading iconal? Now, the sub-leading iconal come from two loops and also as an imaginary part. The imaginary part can be computed from the three-particle cut. So in the unitarity relation, you have this three-particle cut where you have the 5-point amplitude and is given by this expression. So these are the two 5-point amplitude, and you sum over the particle in the middle. And then if you want to do n equal 8 supergravity, this is the sum. You have to sum over not only the graviton, but also photon and scalar. In GR, this is the sum over the two physical polarization of the graviton. Now, if you go to impact parameter, you can derive directly the imaginary part of the two-loop iconal that is given in terms of this of the 5-point function in impact parameter space. And the previous expression is very powerful because it allows to compute directly the imaginary part from unitarity without needing to the complete two-loop amplitude. Now, here you have to sum over the physical state, and in the case of the GR, you have the two physical polarization. In the case of n equal 8, massive supergravity, you have to sum graviton, dilaton, two scalar and two vectors. Now, it turns out that the imaginary part of delta 2 is infrared divergent, it has 1 over epsilon. And it turns out also that the infrared divergent doesn't come from the entire 5-point amplitude. It comes only from the leading soft term of the 5-point amplitude, which is given by the 1 over omega part, which is many people call Weinberg term, and times the 4-point amplitude. And this is the quantity that we want to compute. Now, inserting the leading soft term, one gets this expression for the imaginary part of delta 2. Now, because of the imaginary part, the iconal is not anymore unitary. And okay, this is the way to compute the imaginary part. What about the real part? Now, there is a long history about this real part because the deflection angle at order G cube was computed in a very spectacular paper by Bern and collaborators. And they approximate the two-loop integral in what is called the potential region. So they use the method of the region, and one of the region in which you can approximate the integral, the graviton integral, is called the potential region. And they computed that in the potential region, and it turned out the deflection angle was infinite at high energy, in contradiction with a paper by Amati, Ciafaloni, and Veneziano from 1990, where the deflection angle was computed in the massless case and was finite. So it took about 1.5 years of discussion. Some people were thinking that zero mass and finite mass were very different. Other people thought that one should get the same result. And anyway, the problem was solved because we looked at n equal 8 supergravity, and we added also the contribution of the soft region in the calculation of the looped integral. In this way, one gets an extra contribution, which is called radiation reaction. And when this radiation reaction is added to what one finds in the potential region, one finds a finite and universal deflection angle. The person who immediately understood the meaning of this calculation was Thibaut d'Amour, and he used the linear response equation involving the loss of angular momentum at order g squared to compute the radiation reaction in GR, finding a finite result at high energy. Yes.
You mentioned this was the, well, you borrow the result from n equals 8 or the technique.
The calculation was done in n equal 8 supergravity because there was a paper by Para Martinez, Mao Zeng, that they hold the integral. And so we could use their integral. And then we compute those integral in the soft region. Yeah. Thank you. Now we use...
Paolo, can I ask a question as well? But can you comment please about the... So what was exactly the issue with the result by Bern showing et al.? So were they missing a part of the calculation? Or it's...
No, I mean, they computed in a certain region. In the method of the region, you are supposed to take care of all the region. And they only computed the potential region, and so they missed the region. So the trick was to add the region, and in n equal 8, we had practically all the details, so we could just add the soft region. In GR was more complicated. And what d'Amour did not compute the two-loop amplitude. He found a trick to compute the radiation reaction. And the trick was using the loss of angle. There is a Bini-d'Amour linear response equation that they proved many years ago that involves the loss of angular momentum at order g squared. And through this, they compute the part that was lacking here in the origin, the radiation reaction, and that they added to their calculation in JR, and they found, and he found a finite expression at high energy.
In a sense, I mean, in a sense, the calculation of Bern et al. Was not, it's not that they were sloppy and forgot a region just like that. The resummation to all velocities of result of equal and limit for small velocities. And historically, already there is they use a separation between what they call conservative and what they call dissipative. Especially in this order, it is distinguished because the conservative parts are even in velocity, and the dissipative ones are odd in velocity. So they always did them as separate. So then they did what they wanted to do, which is to resum the even in velocity distributions, and these are all in these potential form. Somehow what missed at the time was that in order to get the high energy limit correct, you had also to add the dissipative. But somehow this was beyond the scope of what they wanted to do in the historical.
Thank you. So we use another method using real analyticity. We show that there is this relation where here you have the imaginary part and there is one that's connected to the real part. Now this bracket is computed integrating over the frequency of the graviton, which is given by this expression. And then we argue that it's this one. But if we go in the region between the two cut, the amplitude is real. And in that region, should have this form. And so when you go over the cut, the cut on the right, you get an I pi that gives this factor here. So from the knowledge of the imaginary part here, we got the real part, and we found complete agreement with Amour. And so this is the iconal a two loop where the black part is the potential region and the blue part is the radiation reaction. At high energy, they get the same behavior for GR, then equalate supergravity, in agreement with the fact that the massless particle with higher spin is the graviton in any gravity theory. And then this is the deflection angle. This is 1 p.m., this is 2 p.m., and this is 3 p.m. Again, the blue is the radiation reaction. This is the probe limit, and this is the green and the black part come from this paper by Bern et al. So anyway, at this point, there was no doubt anymore that there is no doubt anymore that this was correct. And there are several papers that compute completely the two loop, and they managed to extract the quantum amplitude from the complete classical amplitude, including conservative and radiation, and they confirmed the previous result by direct calculation. But now there is a complete result also at 4 p.m. by these papers. And they claim that they included, they have both potential and radiation reaction. And in this case, even if you include the radiation reaction, the deflection angle is divergent. In fact, the deflection angle at 4 p.m. is divergent at high energy. So if you write as a power, fourth power of, you see, at 3 p.m., the deflection angle is just a square of the one at 1 p.m. At 4 p.m., there is a fourth power of this, but then there is an extra sigma, and that means that the deflection angle diverges at high energy. And that seems contradictory with, I mean, this is, how can the deflection angle diverge? And so this is a problem that is still, that people are still working to try find an explanation of this fact. And it's interesting, I don't know if this is very small, it's difficult to see maybe, but this is a paper by these three people where they use the effective one-body method, where if they use just the effective one-body method, it's very, and they want to compare it with the numerical relativity. Now, if they use just effective one-body in a trivial way, they find complete disagreement. So they have to resum. They have to include some resummation, and there are different methods of resumming. And these are the comparison of the numerical relativity are this data here, where there is this plus. And these are the data for different PM. This is low energy, this is high energy. And you see that the green, which is 3 PM, fits, if you go to high energy, fits better than 4 PM. So, and in both cases. So it seems from this data that 4 PM computed from the tree loop that is assumed to be complete doesn't seem to agree with, even after the resummation, with what you get from numerical relativity. So this is a problem left that should be studied further. It's the essentially B, angular momentum of B. Better. If you go to higher, yes. Yeah, this is, they do the EOB, Bonham and Damour. They have different kind of resummation. I show. And I don't know exactly what they did, but they talk about different transformation. What?
Quick comment. Originally, the EOV method was for bonded orbits, right?
Yes, that they also use for scattering now.
So they adapted it.
Yeah.
Okay.
Now, the previous procedure can be extended to the case of spin, and then I'll consider the case of parallel spin, which are orthogonal to the scattering plane. And then in terms of the spin vector, I introduce this parameter A, and then again, using the 1 over epsilon part can be computed directly from the soft theorem, the Weinberg term of the 5-point amplitude, and you get this expression. Now there is the contribution of spin, which is given this formula, where A is the sum of the two spin. And then from the, again, real analyticity, you can get also the real part, which is this expression. And the radiative, you can extract the radiative part of the 3 p.m. deflection angle, which is here. Now, this is valid for any spin, the radiation reaction. The conservative part instead is only known up to a to the fourth. And up to the a to the fourth, if you add the conservative part, the deflection part, there is a cancellation at high energy. However, for higher value of A, the conservative part is still not known. And then using the Bini-Damour relation, which is this, that computes the radiation reaction part of the scattering angle in terms of the loss of angular momentum and the deflection angle at 1 p.m. One can extract the loss of angular momentum as a function of the spin, and one finds this expression that if you put spin to 0 agrees with this other calculation. So now I finish the part of elastic scattering. I don't know if there are other questions.
So they checked the cancellation also in this recent paper of Mao. Ah, okay.
Yes.
Thanks.
So the first, the inelastic observable, I mean, I will consider only this inelastic observable, which is the waveform. And I want to describe two methods for computing the waveform. Actually, for computing the soft part of the waveform, the universal term that you can see that can be resummed. One method uses the word line formalism, and there is a kind of a short review by Ashok Sen from the end of 24, and you can look also the list of early paper using this method. The other method instead is to use the fact that in gravity theory, the infrared divergent only come from one loop diagrams, and that was already in the paper by Weinberg in 1965. Now, for d equal 4 at the 3 level, and for d less than 4 at any loop order, gauge invariance, which is expressed by this expression, fix completely the first 3 order of the expansion of the amplitude around graviton momentum 0 in terms of the amplitude without the graviton. And so you have these 3 terms here. Ji is the orbital angular momentum of the particle I. So this is the leading term, 1 over omega, which is called the Weinberg term. This is the omega to the 0 term, and this is omega to the 1 term. And these are the leading and leading, subleading, and sub-subleading soft factor. So the first two are universal. The third contains only the universal part. I don't know, for instance, here, for the superstring, you don't get any additional term, but you get additional term of the order alpha prime for the bosonic and for the heterotic string. But in D equal 4, so this is valid in D equal 4 at the 3 level and for any D at any order. But in D equal 4, there are infrared divergent, and they were computed by Weinberg in 65, and they modified the soft theorem. So Weinberg showed that the amplitude, the infrared divergent exponentiate times a part which is infrared finite, and the infrared divergent part, which appear in the exponential, is given by this integral. And it also shows that in gravity, they only come from one loop diagram. So if you go to higher loop in gravity, you don't find extra infrared divergence. And this W is given by one loop diagram where the graviton propagator connects two massive lines. So the integral can be computed. You get a real part here, an imaginary part here. In terms of the sigma, can be written more compactly in this way. And here there is, so small lambda is an infrared cutoff, big lambda is an ultraviolet cutoff, and in the dimensional regularization, there is this relation between the infrared and the ultraviolet cutoff and the epsilon. Now, there are small details for G equal K, the imaginary part diverge. So you neglect the imaginary part and compute, and the real part is given by this. And then you can take the limit if one of the particles is massless. In gravity, unlike QED, the limit can be computed because of the absence of collinear divergence. And you get this extra divergent term. It corresponds to one loop diagram where the graviton propagator is attached to a massive and to a massless part. For more recent papers on this approach, you can look at these three papers. Now, in the classical limit, one is left only with the imaginary part, and the classical limit is performed in the way by writing the form momentum of the graviton exchange in this way, and you take h bar to 0, keeping omega finite. It's still quite non-clear why this is a classical limit. We are still working, but that's what everybody says, the classical limit. And then from this, you can write this because n, so this is n, so you have to put W reg, the one which is attached to two massive legs, and then n plus 1, where you have an extra massless particle, and then you can write the soft theorem in inserting here the soft operator, and so you write n plus 1 in terms of m, but now, before there was only the soft operator, now there are all these exponential that you have to take care at the loop level. And then you can compute, you can expand, and you get this term, which is 1 over omega, this term, which is log omega, this term, which is omega log omega square, and those terms seems to be universal. This term is omega log omega, and by explicit calculation, this term has also non-universal term. But I concentrate in this universal term, and I want to also, there are higher order universal terms that I want also to consider. In order to have additional which higher power of this, then you need to construct an extended soft operator. And in the following, I limit myself to this case, 2 in 2 plus a graviton. So an extended soft operator was computed in this paper by these people from Taiwan. So this object is gauge invariant. It's all order in omega, but it's up to gauge invariant terms. So starting at omega square, omega cube, you can add gauge invariant term by, so terms which are gauge invariant by themselves. Now, it turns out that this extended operator should be modified in this way. So that means that to this operator, we must add some gauge invariant term to reduce, to make it to go from this form to this form. And then one gets this extended operator that can be written in a more, using this identity, you can be written in this form. This form is similar to one that Bautista and Guevara wrote, but not quite the same. And then using this extended soft operator, you can introduce here and you can compute additional soft term which have higher power of omega and log omega.
Paolo, sorry, can I ask a question? So can you please repeat what is the rationale behind the addition of the gauge invariant part that modifies the soft operator with respect to the group?
The addition comes immediately. Probably I just yes, I just miss it. Now we construct the amplitude and we check the PN, the leading PN limit. And in the leading PN limit, with the Taiwanese extended soft operator, we got the wrong PN expansion. By changing from the Taiwanese to F, we got the correct PN expansion. That was the first element that we used. So we had to use this gauge invariant term to satisfy PN expansion for small velocity.
Sorry if I. And do you have any additional gauge invariant objects that you can play with, or this fixes completely the form of the extended operator at this PN?
Well, we have not checked the next word. On the other hand, there is another check that we did, which is very non-trivial, that I will come. Let me see. So this is the expression that we got. So it can be resummed, and you see that here it's a resummation of many diagrams because you have a G power in the exponent. So this is a quantity which is, if you want, non-perturbative. And we must use this condition because we want to get rid of the P epsilon in the denominator of this. This P epsilon. And now this calculation can be compared with another calculation done by Fucito, Morales, and Russo, where they solve the Tucholsky equation for the case S minus 2. So the Tucholsky equation, you start from the Einstein Lagrangian, and you expand the Lagrangian around Schwarzschild black hole or Kerr black hole, and you look at the quadratic fluctuation around the Kerr or the Schwarzschild black hole, and this is called Tucholsky equation. Now, if you add the source to the equation that you get, the source essentially represents the back reaction of the particle in the self-force calculation, the reaction of the small particle to the original Schwarzschild-Ocker metric. Now it turns out that if we take our calculation in the probe limit, where self-force is valid, then our calculation agrees with this other calculation. And that's the second evidence why for the correctness of this calculation. Now,
how far can we use this Tucholsky equation method to derive the sub meaning?
well, this is the first order. It becomes more and more difficult if you want to go to the next order.
Yeah. They are all of them computed already.
Which one? Yes. Yeah, yes.
Thanks.
Now, so you can also, it's natural to add the spin here, and it's certainly consistent of quadratic order, but then you cannot cancel this p epsilon in the denominator, and it's not known how to cure this. And one gets similar equation for electromagnetism, and this is being computed in this paper, and for the massless scalar in this paper. So the electromagnetic case agrees with the word line formalist, but the scalar case does not. The gravitational case has been computed only using Weinberg method, has not yet been computed in using the word line formalist. So let me sketch very briefly what word line formalism means for the simple case of the scalar particle. So you have a massless scalar, which plays the role of the graviton, and you describe with a field. And then you have other scalars, which are described by the word line. And then the interaction between the massive and the massless is given by this expression. This is the current generated by the massive scalar. And then this is the formula that you use that is the same using in string theory. It's only here is not tau and sigma, there is only tau. If you have two particles, we have to solve these two equations. They are couple equations. And it can be shown that the equation for the two particles, this is the free case. And then it gets modified by these terms. And you can compute this coefficient. And then you insert this coefficient in the field. And you get that expression. And in frequency domain, you get again a resummation here. And that's what you get from the other method. But here from the word line, you get an extra term. So I came to the conclusion. The two approaches give the same waveform in the case of electromagnetic interaction, while differ in the case of scalar interaction. Only the Weinberg approach has been used for the gravitational case. It would be interesting to understand better the connection between these two methods. So we are checking now that the real classical term is what everybody says to be classical. I have presented only the two case. The case n in m for electromagnetism has been computed in this paper, and in the scalar in this paper, still we are waiting to get the result for n and m in the gravitational case. Okay, thank you very much for your attention.
Thank you. Are there questions? Well, people think about questions. I have one. So in the soft Weinberg part, you mentioned that it was not clear what we would want to call the classical part. I thought that it was, correct me if I'm wrong, but that in the small deflection angle, this piece dominates. Is there something wrong with this?
I mean, naively, it seems that essentially what comes out is order H bar for the rest. And so you neglect. But we have some doubt. Maybe Carlo can explain maybe the doubt because he has been pointing out this.
Yeah, I mean, it depends on what you interpret as being the deflection in the formula that you write down for this soft factor. I don't know, maybe Paolo, if you have it somewhere, one of the resummed any of those in the slides, maybe it helps a bit if you go to the slide. So basically you have P1, P3, P1, P2, P3, P4, and P3, P4 are some deflection of P1, P2, right? Just because they are incoming and then they deflect. So if you regard this formula as a fixed order in the perturbative expansion, then this deflection, as Paolo explained at the beginning, is of order H bar over B. So it's a quantum small effect, and indeed it's true that if you plug in P3 equals to P2 plus H bar over B, etc., you find that what people call quantum is of order H bar. So everyone is happy. Now I guess what Paolo was referring to is that now what we do in this. By applying this procedure that we discussed, essentially what one does is to promote this Weinberg factor to be applied to the classical scattering, in which now P3 and P4 no longer deviate from P1 and P2 by order H bar over B, by this, say, GM over B in the leading order PM or GM over B squared. So there is no longer any H bar. Then naively, if you apply this formula, you would seemingly find a correction that is given by what people call quantum term that is actually of order GM over B. So it's small in the PM limit, but it's classically sizable. So in this sense, there is, I believe it because people shown that in the classical waveform there are only the other ones, not the quantum ones. But it's just, it would be nice to understand it in this formalism that Paolo was showing, why they go away. So we expect them to go away because otherwise they would contradict what we know from the other methods. And okay, this is still something we are trying to figure out.
Yes, David. Let's see if I can hand it.
So I had a question about the waveform part. I mean, so for the conservative part, I understand you're getting information about the potentials and you can take a scattering problem and map it to a bound problem. But for the waveform, is this specific to unbound systems? I mean, scattering problems? Can you take waveform information and incorporate it into, say, a waveform model that people use in LIGO and Virgo?
Sorry, can you repeat? Because
the question is, for the waveform and the memory, can you take this information and apply it to bound gravitational systems as you can with the conservative dynamics, or is the dissipative specific to unbound systems?
this, I mean, we should discuss together.
Okay, yeah, why don't we discuss after?
Yeah.
Sure.
What is the gauge theory analog of the divergence set for PM, like this divergence in the deflection angle?
I mean, that.
Yes, the high energy divergence. Is this understood in the gauge theory case?
Yeah, they computed the complete. And I don't know. I think Sylvie Bern computed in electromagnetism. Yes. Yes.
So I thought, so correct me if I'm wrong, but I thought there are these non-local terms in time at this order.
Which non-local term?
The tail effects, yeah. Okay. We'll talk about it later.
I don't see any further questions or comments. So I guess now we can move to the coffee break and thank Paolo again for the talk.